So yesterday we saw how to, we completed the proof of the Liao inequality. That was the original proof of the Liao inequality. So what I want to do today is to give a different perspective from this result, and also use this different perspective to derive other results. I will first do this in the case of Riemannian manifolds, and then I will move on to more general ambience. So the idea once again is, well, I should say that, what I will talk about is joint work with Fabrice Bourgoin. And our inspiration came from a beautiful circle of ideas that has in fact been developed by Dominique Bacry. So Bacry has been developing for many years, what he called the gamma calculus. And so in the early 80s, Bacry and Emery introduced the so-called gamma calculus. And so the idea of the gamma calculus is the following. Suppose we have a manifold M, and I will start with the Laplacian on M. So I have a Riemannian manifold M, and I have the Laplacian on M. And so the first thing that you have is the Bochner identity, which tells you this. So I've written this identity already several times. So the Bochner identity tells you that on functions, the Laplacian of the length of the gradient of u squared is given by this formula here, which involves the Ricci curvature. So if you look at this formula here, you can say, well, why don't I take it as definition of Ricci curvature? In other words, why don't I reverse this formula, solve it for Ricci, and whatever I have here, then it's going to be something that I need to work with. All right, so I mean, this is in a nutshell the very rough idea. Now let me tell you how to implement it. So first of all, we introduce this object here, gamma of f and g, which, as you will see, in the Riemannian case is just the inner product of the gradient of f with the gradient of g. So gamma of f and g is going to be, so let's look at the formula L, so or Laplacian of f times g. So Laplacian of f times g is f Laplacian g plus g Laplacian f plus twice gradient f gradient g. I'm using this to denote the Riemannian tensor on the manifold. So you say, well, okay, so I want to get a notion of gradient, so I'm going to take the difference of this quantity here, divide by 2, and call it the inner product between the gradient of f and the gradient of g. So gamma of f and g is 1/2 Laplacian of fg minus f Laplacian g minus g Laplacian f. Notice that this bilinear object here is given once you give me a Laplacian. So once you give me a canonical operator on the manifold, I can introduce this gamma object. Okay? So the second step is in this Bochner's identity. So now let's call gamma 2 of f and g. So let's see, we have 1/2 times the Laplacian of gamma of f and g minus 2 times, or if you wish, minus gamma of f Laplacian g minus gamma of g Laplacian f. So, I mean, it will take a little few minutes for you to get adjusted to these gamma notations here, but, you know, notice that in the Riemannian case, this object is just gradient f, gradient g. So you have to keep in mind this fact here. The this thing here in the Riemannian case represents just this. But what I want to emphasize here is that if you give me a second order differential operator on the manifold, I can always introduce this object in a canonical way. This object will depend only on that differential operator. And likewise, this depends also only on the differential operator. Now I will use the notation gamma of f for gamma of ff. Again, in the Riemannian case, this is just the length of the gradient of f squared. And for this reason, this is called, by French people, carré du champ. So the square of the vector field. In this case, the vector field ddxi. And I will denote also by gamma 2 of f, gamma 2 of f. Okay, so let's look a little bit more carefully to this gamma 2 object, and let's try to understand it in connection with the identity of Bochner. So if we use the, so gamma 2 f is going to be equal to 1/2 Laplacian of gamma f. Gamma f, remember, is the length of the gradient of f squared, so I can apply Bochner here. And then I have minus, here I have the inner product between the gradient of f and the gradient of Laplacian g, minus the inner product between gradient of g and gradient of Laplacian f. So in the case in which g is equal to f, I have 2 gamma f Laplacian f. And by Bochner, you see the difference between this object here and this object here is twice the square of the Hilbert-Schmidt norm of the Hessian of f plus twice Ricci gradient f, gradient f. So by Bochner, I can, I have here the distance here, so I have 1/2 and then twice, so I get this plus Ricci gradient f, gradient f. So this gamma 2 object is connected in a natural way through Bochner identity to Ricci. Now let me make another remark. You know, I have already observed yesterday that Newton's identity, inequality tells us that this object here is estimated from below by 1/n times Laplacian of f squared. Okay? So, having made this observation, then we conclude having made this observation, we conclude that gamma 2 of f, here f is just any smooth function of the manifold, can be controlled from below by this object here. Plus Ricci gradient f, gradient f. And now I will introduce a definition. Okay, so definition. We say that M, n-dimensional, satisfies the curvature dimension inequality. Curvature dimension inequality. C, D, rho, n for some rho real number if for any f smooth function on M we have the following. Gamma to f is bigger than or equal than 1 over n times the Laplacian of f squared plus rho times gamma f. Okay, so that's a definition. Now let's see why this definition is interesting. So it's called curvature dimension inequality because, as you will see very quickly, this number rho decides a lower bound for the Ricci tensor on the manifold if you have this inequality here. Okay? So the dimension appears here, of course. And so as I said, you know, the first result that I want to show for you is the following theorem. This theorem is due to Dominique Barclay. And it's a very simple theorem, as you will see. Dominique Barclay says let M be a n-dimensional Riemannian manifold. Then, given a number rho, real number, the following are equivalent. 1, Ricci is bigger than or equal than rho. 2, M satisfies C, D, rho, n. So this is a remarkable fact. This curvature dimension inequality is in fact, which is an inequality on functions, is in fact equivalent to a lower bound for the Ricci tensor. And so let me give you the simple proof. In fact, we are almost there. Suppose that one holds. In other words, suppose that Ricci is bigger than or equal than rho. Then we have seen before, from this derivation here, we have seen before that, you see, gamma 2 is equal to this. But this is always bigger than or equal to this by Newton's inequality. Ricci is bigger than or equal than rho times gradient f squared. This is equal to rho gamma f. So the implication is simply a consequence of Bochner's inequality, Bochner's identity. Okay? So the other implication is a little bit more interesting. So let me show you now this implication here. So let's suppose that the manifold satisfies this inequality on functions, on smooth functions. Let's show that Ricci has to be bigger than or equal than rho. Well, in order to show that Ricci has to be bigger than or equal than rho, what do we need to do? We need to show that for any fixed So fix a point, fix x in M, and let's take a vector in the tangent space. Let's suppose that this is length 1, it's not restricted. Then we need to show that Ricci u is bigger than or equal than rho. This is what we need to prove. Okay? So, now we argue like this. So, let's consider the hypersurface in M, which is orthogonal. So let's fix x0, fix x0 in M, take u like this, and consider the hypersurface in M which is perpendicular to u in x0. Okay, so let's look at, so I'll write it as script f. Script f is the collection of points in M outside of the cut locus of x0 such that x at x0 to the minus 1 of x is perpendicular to u. Okay? And so, remember, down here there is M, so here is point x0, we have the tangent space, and we have the exponential mapping, which locally is a diffeomorphism. Okay? So the exponential mapping is a local diffeomorphism from the tangent space to the manifold M. So I'm taking a vector u, the tangent space, so I have this script f. So now I take f0 to be the sign distance function from f. So f0 is defined on M minus the cut locus of x0, the values into the reals. And I take it to be f0 of x is equal to the distance of x to f times the inner product, or actually the signum, so the signum of the inner product between u and x x0 to the minus 1 of x. Okay? So this sign distance in a sufficiently small neighborhood of x0 is a smooth function, because the distance function is smooth on a manifold when you stay away from the cut locus. So that is a smooth function, and so certainly there exists a sufficiently small neighborhood u of x0, so there exists u of x0 sufficiently small such that f0 is C-infinity in u. Okay, now I don't have, f0 is not C-infinity on the whole manifold, because when I hit the cut locus that is only Lipschitz. However, I can use a standard argument with the cutoff function to extend this function f0 to a function which is smooth on the whole manifold and which has at x0 the properties that I'm going to state by now. So, and moreover, so you have to think of this f0 like an analog on the manifold of a linear function. So, and moreover, here A the gradient of f at x0 is equal to u. B, the Hessian of f0 at x0 is 0, so f0 is flat at x0. And C, this is almost obvious by the construction, the gradient of f0 at x0 in length is equal to 1. Actually, this is true in a neighborhood, so for any x in U. Okay, so these things are classical properties of distance function. So at this point, we are finished. At this point, we are finished because we look at Ricci of u. This is Ricci of gradient f0 at x0. Gradient f0 at x0. And this is equal, I'm afraid that it's gone from the blackboard. So remember, this is equal by the identity that I proved before. If you solve for Ricci, the identity I showed you before, so I showed you before the gamma to f is equal to 2 plus 2 Ricci. So if we solve for Ricci here, we get that this is equal to 1/2 gamma 2 of f0 evaluated at x0 minus, so let's see, minus this thing here. Okay? On the other end, by property B, this thing is 0. And I'm assuming the curvature dimension inequality that tells me that this is bigger than or equal than 1/2. So then I have here 1 over n Laplacian of f0 at x0 squared plus rho times there is a so let me see, there is something that is weird here, and it's this. The way I defined gamma 2, there were no 2's anymore here. Otherwise we get the wrong number for the curvature. So I apologize, let's remove this. Okay? So we have this, and then there is no 2 here. And then we have rho gamma f0 at x0. Again, by this property here, the trace of the matrix is, which is the Laplacian, is 0, so this is gone. And so we get that Ricci of UU is bigger than, this is 1 because of this, and because of my choice of U. Okay? So this is equal to 1. And so the conclusion is that Ricci of UU is bigger than or equal than rho. End of the story.
And in sub-Riemannian case, do you really have some problem with cut losses?
No, in sub-Riemannian case you do something different. Okay, I'll show you what to do. It's more complicated than this. Okay. All right. So at this point, we have seen that. Question? No. We have seen this interesting fact that lower bound on the Ricci tensor is equivalent to this curvature-dimension inequality. So this curvature-dimension inequality completely captures lower bounds on Ricci tensor. All right, so now let me bring in the main character of my discussion, the heat equation. Okay, so now I am on a Riemannian manifold M, n-dimensional, and there is the Laplacian. I'm assuming the Laplacian is self-adjoint operator, so there is the Riemannian volume on M, and I will look at heat semigroup generated by the Laplacian, which I will denote by PTF. So of course this is a new function which should be evaluated at any point x. So we know that the semigroup is sub-Markovian. So PT of 1 is less than or equal to 1. That's always true. What is not always true is that the semigroup is Markovian, okay, or that this is not always true, okay. So I will talk about this later on, but for the purposes of my discussion, I mean, this will be automatically always true, given the assumptions that I made on the manifold, because Xing-Kun Yao has proved in mid-70s that if Ricci is bounded from below by a constant, any real number rho, then PT1 is equal to 1. So we get the same property that we have in Rn. In Rn, we know that if we take the heat kernel and we integrate it.
Excuse me, Nicola.
Yes.
But PTF is defined only for f from L2.
Yeah, well, it's defined only for f. Originally, you can define only for f which are continuous with compact support, let's say.
Yeah,
but then you can extend it to bounded function. Okay? So you can actually extend the semigroup to L infinity. So we have this property here. And this is what this is telling you. Okay? But anyhow, I will not
Rho is arbitrary, positive.
But rho is arbitrary real number. This is the theorem of Yao. Yao proved that if you have a complete Riemannian manifold with Ricci bounded from below any number, then the semigroup is Markovian. PT1 is equal to 1.
Particularly that is true for compact.
Yes. Okay,
What is the physical sense of this?
this is tells you something about blow up in infinite time.
If you have constant temperature at the initial moment, nothing will happen
Yeah.
forever.
Yeah.
Why the theoretical condition is needed?
Well, this is actually, as you will see later, I mean, it's actually a very important property. So, well, as we all know, the heat equation is not physical because it has infinite speed of propagation. Heat does not propagate at infinite speed. However, for the heat equation, heat propagates at infinite speed. Because if I have, suppose I have a device and I have a little source of heat here, then if I write the solution, my solution of the heat equation, so it's dxy p f of y dy, no matter how small this source of heat is, as soon as t is bigger than 0, I will feel it anywhere. This is against physical reality, right? Heat does not propagate.
But physicists are not confused with this.
No, they're not confused because they use the heat equation nearby the source of heat. And nearby the source of heat is good. Nearby the source of heat is very good. And for small times. But otherwise, I mean, you have to complicate the heat equation considerably. You know, it can't be just Laplacian. It has to be much more complicated already. But, and this infinite speed of propagation has to do with this Markovian property. But anyhow, so there is a function. So this is a C-infinity function on M cross M cross M minus the diagonal cross 0 infinity. Okay? So, it's symmetric, and it's positive, strictly positive. C infinity comes, I mean, this is a deep consequence of, elliptic theory on the manifold. Essentially the fact that the Laplacian or the heat equation is a hyperelliptic operator, so it smooths out. So, but I mean, this is classical stuff, so I'll take it for granted. So let me consider then the heat semigroup, which is defined like this. So f of y, and then I have p x y p d mu y. So I will put I will endow the manifold with its Riemannian volume so that the Laplacian is self-adjoint with respect to that measure there. Okay. So we have this operator here, and now let me just observe that if we look at uxt equal to ptfx, then u satisfies the Cauchy problem in m Cartesian 0 infinity, and u at time 0 is equal to f. At least if f is sufficiently okay. I mean, I cannot take f too wild at infinity. All right. So now I will start introducing, my main characters. So I fix t bigger than 0 and consider let me see, how do I want to denote this? Let me consider v of xt to be t minus little t of fx. So notice that now time is reversed. Okay? Heat semigroup is defined for the value of time bigger than 0, so this is defined only when little t is strictly less than capital T. So this function here, it's a smooth function in C infinity m cross minus infinity capital T, and it satisfies the backward heat equation. Notice here there was a minus, now here there would be a plus. So in m Cartesian minus infinity capital T, and v at time capital T is equal to f. So now we're looking at this situation. So here there is m, here there is time, so I fix a capital T, and the equation is evolving in this direction now. Okay? Because of this time switching here. So that's all that there is. Okay, so now let me introduce the two objects which in the Riemannian case were introduced by Cree and Emery. So what I'm telling you now is a story which is already known up to now. Then there will be a new twist. So I will tell you when the new twist happens. Okay, so so let me assume that f is a function which you can see 0 infinity of m and bigger than or equal than 0. Now I have to be careful a little bit with the fact that I'm allowing f to be 0, as you will notice, but because of what I'm about to say. And I consider this functionals. So psi of t, this I should write psi of t at x, but as a rule I will omit the x, okay, just for simplicity. So psi of t is going to be equal pt of t minus t f times the log of p minus p f, evaluated as x. The reason for this functional here is by Cree and Emery, they were interested in hypercontractivity estimates, and so they come from there. But I will use them in a different way. Okay? So we have this is definition. And then I will define capital phi of t to be pt of p minus pf times gamma. Remember, gamma is the length of the gradient squared of a function. Gamma of the log of p minus pf evaluated at x. All right? So let me say a few things about these two objects. First of all, let's observe what is psi at 0. When t goes to 0, remember pt picks up the initial value. So I have to put the initial value of this function at t equal to 0. When t is equal to 0, I pick up p capital Tf, so this is equal to p capital Tf. I will omit x. Everything is calculated at x, okay? So for simplicity, I omit that. And then I have log of p capital Tf. Okay, so that's what we get at 0. Now let's see what we get at capital T. So when I go to capital T, this goes with continuity to capital T, but this goes to 0. So I pick up the initial value. So I get P at capital T F log of F. Okay? Now let's look at phi. Phi is 0 is equal to, once again, when t goes to 0, I pick up the initial value of this function at time t equal to 0. So at time t equal to 0, I get ptf gamma of log of ptf ft, instead, I get pt here. Here I pick up the initial value, f, and here I get gamma of log of f. Okay, so,
You mean field of phi.
oh yeah, this is it. Thank you, thank you. Hopefully there will not be too many of this today, with 3 hours. Oh, by the way, what time am I supposed to stop? Because I'm sorry, I keep going. Soon? Yeah, let's stop here. Okay, let's stop here, and then So here is the lemma, which is again a calculation, but it's an important lemma. Well, you have to remember this thing here, this equation here, because I will use it. Okay. So lemma, again this lemma is due to battery, and it says the following: part 1 psi prime is equal to phi. So the derivative of this functional psi is equal to phi. Part 2
Derivative by t?
in t. Here we think that x is fixed and we are differentiating in t. So part 2 is just a consequence of part 1. So we take the integral between 0 and t of phi, and this is equal to, well, as you can see, this is equal to, according to part 1, in the fundamental theorem of calculus, is psi of t minus psi of 0. And now you just replace the value of psi of t, the definition, and psi of 0 is this one. So the statement is this. I will not write it, because it's just copying what is written on the blackboard. And part 3, which instead will be very interesting to us, is that the derivative of phi, again, the derivative in t, is equal to twice pt t minus t of f, and here there is gamma 2 of log of t minus t f. And again, this is evaluated at x. X is fixed here. Okay. So let me see if I can work out the chain rule, because this is an exercise in the chain rule. So let's start with part 1, proof. But notice that, and this is the relevance of gamma and gamma 2. These are like the higher order symmetric functions of the Laplacian. So, so we start with phi having in the definition gamma, we differentiate in t, and gamma 2 appears here. Okay? So that's where the curvature starts appearing. Alright, so let me do the proof then. Unfortunately, I have only these 2 blackboards, so I have to be very careful with the space. So, well, so first of all, psi prime. So psi prime, we have to differentiate first this object, and then we have to put the derivative in t under the integral sign. So we get ddt of pt of pt minus df log of pt minus df plus, and then I have pt, then I have ddt of what we have under the integral sign. So pt minus df log of pt minus df. Okay. Now remember that
First term dt of pt applied to
exactly.
probably
So this is, think of this as a, you know, as a, I don't know, function g. So if I look at ptg, g is this function, okay, which of course depends also on t, and this is why I have to put the derivative inside the integral. Okay, so as a function of t and x, this satisfies Laplacian of ptg equal ddt of ptg. It satisfies the heat equation. Okay? So I can replace this ddt of pt applied to this function with the Laplacian of pt applied to this function, because it satisfies the forward heat equation. Is everything clear at this moment? Okay, so let me do it. So I get here equal to the Laplacian of pt applied to my function inside log pt minus pf plus pt, and now let me take derivatives here. So one time I put the derivative over here, the other time I put the derivative over here. Okay? So I get ddt of pt minus df times the log of pt minus df plus pt, and then I have pt minus df times ddt of the log of pt minus df. Maybe, yeah. Okay, so the next observation is that Laplacian and pt commute. The Laplacian commutes with pt, because this is simply differentiation under the integral sign. Okay? So I can rewrite this as pt of Laplacian of pt minus df times the log of pt minus df, because pt and Laplacian commute. Just think of it, the Laplacian of pt g at x is equal to the Laplacian of the integral of p x y p g y d mu y. And this is the same as the integral, because this is a symmetric function, is the integral of p x y p Laplacian of g y d mu y, which is equal to pt of Laplacian g x. So I can bring the Laplacian inside. Okay? So Now, as for this term here, I have ddt of the logarithm. So the dt of the logarithm is ddt of this object divided by the object. And here I have the same thing. So this quantity here simplifies in ddt of p t minus t f. Is it clear? ddt of the logarithm is ddt of the function divided by the function. But then I have the same function here, so they cancel, numerator and denominator cancel, and I'm only left with this inside the parentheses here. So, so that means that I unfortunately have to erase here. So what we get then is that psi prime of t is equal to pt of the Laplacian of p minus t f log of p minus t f plus pt of remember now, I'm going to make a remember that this function here satisfies the backwards equation. So remember that v of xt equal to p t minus t g x satisfies the equation Laplacian v plus pt equals 0. So ddt of this object is equal to minus Laplacian. So I will write here minus pt of Laplacian of p t minus t f times the logarithm. So times the logarithm of p t minus t f. Close parentheses, and then we have plus pt of, as we said, we just have this thing here. So of ddt, once again, this is minus Laplacian of p t minus t f. Because these two things combine into this one, but then ddt of this is minus Laplacian because of this equation here. Okay? Right. Okay, so now let me see if we can start simplifying a few things. Now we have the Laplacian of a product, so Laplacian of capital F times capital G is F times Laplacian G plus G times Laplacian F plus twice gradient F gradient G. Okay, so this thing here is equal to Pt of, so I have Laplacian of pt minus tf times the logarithm of pt minus tf, first term. Then I have plus pt of, so I have this times the Laplacian of this pt minus t Laplacian of log of t minus t f plus twice pt of. So I have the gradient of this inner product with the gradient of this, that is just gamma. Remember that.
You missed F.
Where? Yes, thank you. So plus I have twice pt, and then I have gamma of pt minus t f, and then log of t minus t f, close here, close here. Okay? So that takes care of the first term. Then we have the second term, which is minus pt Laplacian of pt minus t f times the log of pt minus t f. And then we have the third term. For the third term, pt and Laplacian commute, so I can take this out, and then the semigroup property pt or p capital T minus little t becomes p or capital T, so I get minus Laplacian of p capital T f. Is that clear? Because these two commute, so this comes out, and then I have the semigroup p little t times composed with p capital T minus little t, that just gives me p capital T f. Okay? So let's see, something simplifies here. We can cancel this one and this one. Okay. And now we are left with this one and that one. So let's see what we do with this object here. Did I take care of everything? So these two are gone. Then I'm left with this and this. Well, I guess that I should, I want to prove this, right? So let me recall what is phi. Because somehow here we must show that the sum of these three terms adds up to phi. So let's recall what is phi. Recall that phi of p is equal to pt t minus t f gamma of log of t minus t f. Right? Let's check that that is the correct definition. Okay? So let's see. We have to do something here. We have to do something, and let's do something with this object first. So the Laplacian, so let me do it here. The Laplacian of log of t minus t f. So I have the composition of a function with another function on the line. So it's the second derivative of this function times the length of the gradient square of this one. So this is equal to, so the second derivative is minus 1 over t minus t f squared. And then I have the gradient square of this function, which is gamma of p minus p f. And then I have plus the first derivative of this function times the Laplacian of this. So plus 1 over p minus little p f times the Laplacian of p minus little p f. So this is the object that we have in here. Notice that when I multiply by p minus little t f, this one, okay, something interesting happens, because so I'm multiplying this object by this. So when I multiply this term, I simply get the Laplacian of pt minus little t f, and I have pt of the Laplacian, so I have again pt of the Laplacian of p minus t f. Again, Laplacian and pt commute. This is Laplacian of p minus t f. So this is the Laplacian of pt f. I have minus Laplacian of pt f, so this term cancels. This term is cancelled by this one. Okay? So allow me not to write everything, otherwise you will fall asleep if I write everything. But so I have to substitute this object here with this. And you see, the second object here, when I multiply it by this, I'm left only with this one. This one is equal to this, and this is cancelled by this. So I can, let me do this. So the other term is PTF multiplied by this. So we get equal to minus, so I have PT of, I have the square there, so when I multiply by this, I'm still left with one of these guys. And then I have gamma of P minus P f. Okay? Plus twice PT. So let me erase this. We are almost finished. So let's look at this thing for a moment. I have gamma of pt minus little t f log of pt minus little t f. So this thing here, just this one inside. Remember, this is the gradient of this inner product with the gradient of this, but the gradient of this is the gradient of this divided itself. So this equals twice pt, and then we have gamma of pt minus little t f divided by pt minus little t f. Is it clear? Chain rule. I'm taking the gradient of this thing here. This is an inner product of two gradients. Okay? So the gradient of this is the gradient of p divided by p. Okay? So I can, this term here is equal to this. And now let's compare. So, okay, so I get 2pt, and then I get 1 over pt minus little t f, gamma of pt minus little t f. Okay, so these are the same, except that there is plus 2 here and minus 1 here. So this equals pt of 1 over pt minus t f gamma of pt minus t f. And we're finished, because that is the same as this. Again, This is gamma of log. So this thing here, if you convert it, would be gamma of P minus Tf divided by P minus Tf squared, because you have two gradients of this guy. This is gradient of this, inner product with gradient of it. So one time you get gradient of this divided by Pt, inner product with gradient of this divided by Pt, so you get gamma of Pt divided by Pt squared. You have a Pt here, they cancel, we are left only with one Pt in the denominator, so that means that this expression is equal to this expression, so 2 minus 1, so you get this, and then this is equal to 5. And we're finished, at least with this calculation. Okay? I promise that this is the most technical lemma today. Unfortunately, you know, this is Chengdu doing the calculation over and over, and hoping that you are lucky. Because, you know, if you don't see what you have to do at every step, then it's a mess, you have to redo everything. I've done these calculations many times. So we have proved this one. As I say, this one, there is nothing to prove, because it's just 1 plus the fundamental theorem of calculus, okay? So let's prove now 2. 2 is a little bit more involved, because we have to make a gamma 2 appear. So I have to hope that I'm even luckier than in the proof of 1. And if you don't want to see the proof of 2, I can skip it. I mean, I will gladly skip it, but I'm joking. I will prove it, okay? Because it's, you know, it gives us, it allows us to become familiar with this gamma calculus and how the quantities interplay. Once that we have this lemma, then you will see everything becomes much easier. Okay, so now let me keep the definition of phi here, because I have to differentiate it. I will probably need to get this. Oh, I can go on.
Don't worry.
Thank you. Thank you. And maybe, yeah, maybe we need some light. So now I have to show for you that when I differentiate this object, I'm going to get this one with the gamma 2 here. As I say, you know, this is a little bit technical because it's calculations, and thank you so much. And once that we have this lemma out of the way, then things become much easier. So let me erase this stuff here, erase this stuff here, and erase this. So let's start looking at 5 times t. Again, you know, I have to do the same game as before. So I have to take the derivative of this. And then I have to put the derivative inside, plus pt times ddt of dt minus tf times gamma of log of p minus tf. This quantity is this operator pt. You know, plays an important role in many questions which have to do with log Sobolev inequality, ultra contractive estimates, and so forth. So it's a miracle operator, and you will see that it really does miracles at some point. So, all right. So let me start with the first. So we move on like before. ddt of pt of a function is equal to the Laplacian of pt, and then Laplacian of pt is pt of the Laplacian. So I can do it directly this time. You will accept that this is equal to this times the Laplacian. Let me see if I want to do it this way. I guess I want to do it this way. I want to do it this way. Yes. So the Laplacian of pt minus little tf times gamma of the log of pt minus little tf. So let's see, let's put a parenthesis here. So we are taking the Laplacian of the product of these two functions. We are taking pt, and then here I have pt of this. So again, I put one time I put the derivative here. So I have pt times the derivative of this. The derivative of this, remember, is equal to minus Laplacian of this. So I will write immediately that this is equal to pt of Laplacian of pt minus tf times gamma of log of pt minus tf. And then the other time I put the derivative over here. So I have plus pt of p minus tf times ddt of gamma of the log of p minus tf. So let's see. Is this clear enough, or is it confusing? This is ddt of this function here. Okay. So I think I put everything now. All right, so we don't have any much choice. We have the Laplacian of a product. So once again, we have to take, so I have to take the Laplacian of this times this. So I have pt of the Laplacian of p minus tf times gamma of the log of p minus tf plus pt of p minus t, the Laplacian f times the Laplacian of gamma of the log of p minus tf. Let me tell you, if you're wondering where is this guy going to come out with, notice that here I have Laplacian of the gradient square of a function. That is connected via Bochner's identity to gamma 2. And that's where the gamma 2 will come out from. Okay? So this is, so we have this term here, and then we have plus twice. So I have the inner product between these two things. So I have twice pt. And now the notation gets a bit complicated. The inner product is a gamma object. So I have gamma of p minus little tf, and then I have gamma of log of p minus tf. So I have gamma of this. So this is one function and this is another function. And let's put a third parenthesis here. Okay, so we took care this, and this takes care of the first term. The second term, we keep it the way it is right now. So then we have minus pp of Laplacian of p minus little p f times gamma of log of p minus little p f. And the third term, we make the observation that so ddt of gamma of two functions, I'm going to call them g and h.
Nicola,
Yes.
in the previous term, Laplacian acts on...
Laplacian acts only on this function here.
Probably some kind of...
So maybe you prefer to have a parenthesis here. Okay? So if I do this, this will be equal to gamma of dg dt h plus gamma of g dh dt, right? Because this is an inner product. These functions depend on t, so I have gamma of dg dt h plus gamma of g dh dt. So that means that, well, here I have one single function. So if I have one single function, so if g is equal to h, then I have here twice this. Okay? So I'm going to apply this observation to this object here. So we get, let's see, where is the equality? Right here. So I'm writing the last term. So I get plus. So this last term, I can write it as twice pt p minus pf. And then I have gamma of p minus pf, comma d p minus pf. So I have used this observation to rewrite this term in this way.
How about the logarithm?
Divide.
Let me see. Oh, wait. The logarithm. You're absolutely right. Where is our logarithm? It's gone. That would be a bad idea. So we have gamma of log of this, and then here we have ddt. Is this what you were worried about, Vladimir?
Yes.
Thank you. I will be worried too, because we will be in trouble if this guy is not here. So, all right. So this should be okay now. Okay, so let me erase the observation down here. Okay. So let me see. Now something must happen. So let's see, what is it that we can erase before we start getting involved with that guy over there? Let's see.
The first one and this fourth.
This one? Yes. So we can erase this and this one. Right? So that one is gone. this one we want to keep because it's going to give us the gamma 2 plus other stuff. And let's see, what else can we do with this stuff here? I think that we probably can do, let me think for a second. So maybe that we can connect these two terms here. Although I'm worried about the sign of these two terms. The two terms with the 2, they have the same sign. Okay, well, it's what it is. So let's keep everything as it is right now. Let's remember that the equality starts here. And let's work out this guy here. So let's write this guy. So Laplacian of gamma of log of p minus little p f. So this guy is equal to twice gamma 2 of the log of p minus little t f plus twice gamma of, so I am essentially rewriting the definition of gamma 2, plus twice gamma log of p minus little t f, Laplacian of log of p minus little t f. Okay? So I want to substitute this information now into this term here. And let's see what happens. So let's use, I'm going to erase everything here. So we can now use this complete blackboard. What we have so far is that phi prime t is equal to. So this is gone, so this one is substituted by this. So we have 2 pt t minus t f times gamma 2 of the log of t minus tf. When I substitute this into here. And remember, I want to show that phi prime t is equal to this. So everything that comes afterwards must add up to 0. Okay? Because this is, if you check the statement, part 3 of my lemma is to prove that phi prime is equal to this. So I want to show that everything else adds up to 0. Okay, so that is, so we get this term from here. Then we have 2 times pt of this mass here, so plus 2 times pt of p minus little p f. And then I have gamma of log of p minus little p f inner, well, not in, well, it is an inner product, Laplacian of log of p minus p f. Close the parentheses here, close parentheses here. So this takes care of this term here. Now we have this, so we have plus 2pt P minus P F, and then we have gamma of log of P minus P F, comma, ddt. Okay, so once again, the ddt of this is going to be ddt of this divided by this. So let's see how we can, because I want to make the Laplacian appear. So
Excuse me, but you missed the previous term.
where?
The second.
So this one,
Yes, you
we
rewrite.
put this one and we put this one, it's here.
Oh,
and then we put this one.
This one myself.
So these two are, they are already in. So these two terms here replace this one.
Yes, I understand.
Now I'm looking at this one.
Oh, you look at this one.
Okay? So are we okay?
It seems you're looking at the next one. not this one.
Well, let me see. So this one gets replaced by these two objects, and they are both here. Then I'm looking at this one here, and I have, ooh, did I skip one?
No.
Oh, I see. Well, let's put this term in here. So we have 2pt gamma of P minus Pf, and then we have gamma of log of P minus Pf. Okay, so this is gamma of these two functions here, so we close here and then we close here for the pt. So that takes care of the second term. And now let's look at the third term. So before I write it down, ddt of the log is going to be ddt of this divided by this. Okay, but ddt of this is equal to minus Laplacian of this. So I'm going to put a minus 2 here. I'm going to put a minus 2 here, pt, and then I have pt minus little pf, and then I have gamma of log of p minus pf, comma, and then I have the Laplacian of p minus pf divided by p minus pf. Okay, so I hope we have put everything in. Is this clear what I've done here? I have taken the derivative here, so ddt of this divided by this, but ddt of this is minus Laplacian, so I've taken the minus out. Okay. So at this point, let's note a few things. Okay. So let me see. Where is it that we can do something else
We
before?
should write down Laplacian of log.
Yeah, I should
Yeah.
write down the Laplacian of the logarithm. And
It's
it's gonna, so what I want to show now is that this plus this minus this is equal to 0. And it will work out. Okay? So in order to accomplish this, we just write down the Laplacian of this. So the Laplacian of the logarithm of p minus pf, we've done this before already, is minus 1 over p minus pf squared times gamma of p minus pf plus 1 over p minus pf times the Laplacian of p minus pf. Okay? This comes from the chain rule. And now you see that if we start combining things, if we put everything together, so let's verify this, because at this point we should be able to verify. So let me erase this, because we don't need this blackboard anymore, so I can erase it. Hopefully there is no mistake there coming from here, because otherwise we have to go back, and that would be a disaster. Okay. In this calculation, one has to be just a little bit patient and careful. But I think that at this point everything would work out. So, if we replace in here this object with this, so we get, so I'm just going to look at this, at the first object. The first object becomes minus 2pt. The minus comes from here. Okay? So minus 2pt. Then I have p minus pf here. And then I have gamma of this. So gamma of this, let's see. So let me be a little bit careful here. So let me write 1 over pt minus pf squared coming from there, and then I have gamma of this guy here. Gamma of this guy, so this is going to be gradient. So I'm going to get the gamma of this divided by this. So why don't I put here a cube, and then I have gamma of p minus pf, comma, gamma of p minus pf. So these are the two functions, so we close this and then we close this. So the first term, so this produces that object there. So then I have the second term. The second term produces plus 2pt, and again I have p minus pf here, and now I have 1 over pt minus p, so I'm going to write it as 1 over, and I will explain. Like this, gamma of p minus pf, and then I have Laplacian of p minus pf. So close here and then close here. So where does the square come from? I pick up 1 from here, from this term, but then I also have the gradient of this. The gradient of this is going to be the gradient of this divided by it, and so I get the square here. Okay? So are we good? So the first, this term here is converted into this 2. Now let's look at the second term. The second term, you see, gamma of this, again, I'm using the same gamma of log of t minus tf. So this is the gradient of this inner product with the gradient of this, that is the same as gamma of t minus tf divided by t minus tf squared. Okay? So, so for this term here, I get twice, so plus twice pt, and then I have plus twice pt of gamma of pt minus tf inner product gamma of t minus tf closed, everything divided by p minus tf squared. That comes from here. That comes from this guy here. Okay? And then finally I have minus 2 pt pt minus tf, and then I have gamma of this. Gamma of this is going to be gamma of this guy divided by this guy. So, and I have an extra guy here. So I have pt f, and then I have 1 over t minus tf squared gamma of t minus tf times comma Laplacian of t minus tf. And now let's hope that there is a divine justice. So this and this is squared. There is a minus, there is a plus. So this term and this term cancel. Okay?
Excuse me, why
Just 1 second.
cube by square?
What?
Why did you replace?
Where?
The first line.
This one?
The first line.
The-
Cube by.
Oh, there is a p1 and there is a denominator with power 3.
Oh, I see. Okay.
This was simple. This was a simple one. So this and this cancel, and these two here also cancel, because you see and we got the same thing, but there is a minus here and a plus here. So, and we're done. So phi prime is equal, so this is gone, this is gone, this is gone, and we're left with this, which proves